Hello everyone, so today we are going to solve two problems from Irodov. As usual, I have the first problem written down there. I'm going to read it out and explain it to you. So in this problem, I have a small body A that starts sliding off the top of a smooth sphere of radius r. Find the angle theta corresponding to the point at which the body breaks off the sphere as well as the break off velocity of the body. Okay, so in this problem, I have a sphere. Okay, hemisphere to be very honest, and I have a body on the top. Let's say this is my body. Let me paint it with green, and it starts sliding on the top of this sphere. Okay, uh, something like this, and it is at this point, let's say, wherein it loses contact with this sphere and it leaves the sphere with a velocity of v. I need to find out the angle that this body at this point makes with the vertical. So I need to find out this angle theta, and the second thing that I need to find out is this velocity v. These are the two things that I've been asked to find out in this question. Okay, I've not been given any mass. Okay, so let me assume that its mass is m, and based on this information, let me solve this problem. Okay, so the first thing that I have to figure out is what exactly is happening at this point. Okay, that is the point wherein the body of mass m is about to leave the sphere. So if I observe that particular point, the normal force between the sphere and the body is going to be equal to 0, since the body is about to leave the sphere. Okay, and if I observe the body, there is a force that is mg acting in the downward direction. There is a component of the force, okay, there is a component of this force mg along this direction, which actually is acting as the centripetal force, which is required for this body to move in a circular path at this particular point. Okay, if this angle is theta, then this angle is also going to be theta. This is the direction of mg, right? This is the direction of mg. I need to find out this component of mg. Okay, so that component is nothing else but mg cos of theta. Okay, this is actually providing the centripetal force to this body. So the centripetal force is mv square by r. Okay, so this is my first equation. The sphere is frictionless. Okay, it has been mentioned in the question that it's a smooth sphere, which means that it is frictionless, and it has got a radius of r, by the way. Okay, it has a radius of r. If I observe this body, it has fallen by some height, right? Which means that it has lost some potential energy. What is the height by which this body has fallen? If you calculate this height, it is r into 1 minus cos of theta. It's pretty simple to calculate, you can do that. So the net loss in potential energy is going to be equal to mg times r into 1 minus cos theta. This should be equal to the increase in the kinetic energy of the body, which is going to be equal to half times mv square. Okay, if I remove this r and if I bring it down, this is, let's say, my equation 2. Okay, I can replace this part, that is mv square by r, by mg cos of theta, right? So this gives me mg times 1 minus cos of theta is equal to half into mv square by r is nothing else but mg cos of theta. Okay, I get mg cancelled from both the sides, which gives me cos theta as 2 by 3. Okay, which means theta is equal to cos inverse 2 by 3, which is nearly equal to 48 degree. Okay, so this was the first part of the question wherein I had to find out the angle with the vertical that this body makes while it leaves the sphere. In the second part of the question, I have to find out the velocity with which it left the sphere. That can be easily evaluated by this expression. Okay, so I just need to put in the value of cos of theta there. If I put in the value of cos of theta equal to 2 by 3 in there, I'll get mg divided by 3 is equal to half times m v square by r. M gets cancelled on both the sides, which gives me the value of v as 2 by 3 times r g to the power 1 by 2. This is what the velocity of the body is going to be when it leaves the sphere. Okay, so this is what my first question was. I had to basically use the conservation of mechanical energy to write down one equation. The second equation was written on the basis of the centripetal force, basically circular motion. Okay, let's move down to the second question. In this question, I have a device that consists of a smooth L-shaped rod which is located in a horizontal plane, and a sleeve A of mass M is attached by a weightless spring to a point B. The spring stiffness is equal to x. The whole system rotates with a constant angular velocity omega about the vertical axis, passing through the point O. Find the elongation of the spring. How is the result affected by the rotation angle? Okay, so let me first draw the diagram. Okay, I'll draw it with a pen. So let's say this is my vertical axis about which my L-shaped rod is rotating, and let's say this is one end of the rod. I'll have to rotate it a bit. Okay. Oh no. Yeah, let's say this is my rod. Okay, and let me draw the other end of the rod. Alrighty. Alright, so this is my rod, and I have a body of mass m attached with this rod. Okay, so it has a mass of m. I've been given that information. Okay, and it's not exactly attached, it's allowed to move freely along the rod. Okay, and this body is also attached to this point B. This is, let's say, point A. This body is attached to the point B via a spring. Okay, and this whole system is moving, let's say, in the anti-clockwise direction with an angular velocity of omega. Okay, so this is a kind of a 3D view of the diagram. If I draw the 2D view, it would be something like this. I would have a rod. Okay, L-shaped rod. Alright, I'll have my mass m attached at this point. Okay, this is going to be my point B, and I'll have a spring. Okay, this is the point about which this rod is rotating with an angular velocity of omega. This is what my setup is going to be. Okay, given this information, I have to find out the extension of the rod. Okay, so let's say that initially when the rod was at rest, m was at a distance L. Okay, and the spring was also at rest. It was not moving, as in it was not under any extension or under any compression. It did not have any extension or have any compression. Okay. This was the initial situation wherein my body was not rotating. Okay. Once it started rotating, okay, so I'll copy this diagram. There has to be some kind of extension, right, in the spring. So once it started rotating with an angular velocity of omega, this mass m would have underwent some movement, or there would have been some extension in the spring. Let's call it delta L. Okay, and the mass now is at this point. Okay, the spring has extended. Okay, all right. So in this situation, let's say that sorry. Let's say in this situation, the angle between made by the body with this part of the rod is, let's say, theta. Okay, now let me observe this mass m. It is rotating about this point with a radius, let's say, p. Okay, since it is rotating, there has to be some centripetal force on this mass m. Okay, now let me observe this mass m. What are the forces that are acting on this mass m? If I observe this mass m, there is a spring force which is equal to x times delta L, which is acting in this direction. There is no other force that is acting along the rod, okay, because the rod is frictionless. But there is a normal force that the rod is applying on this mass m in this direction. The centripetal force, which is along this direction, is a result of both these two forces. Okay, so if this is the case, let me write down the centripetal force first. Okay, what would be the centripetal force? If its mass is m, if the radius is p, if the angular velocity is omega, the centripetal force is m into omega squared times r, which is p in this case. Now this r has got two components, right? Actually, this r is a resultant of these two components, right? But if I consider this basic concept wherein, let's say, I have a vector a in this direction and a vector b in this direction, and I have a resultant r, and let's say this angle is theta, then I can write down the magnitude of b as r cos of theta, and the magnitude of a can be written as r sine of theta, right? So the same concept I'm going to apply here as well. I'm going to find out this component of the resultant, which is m omega square into p. This is the resultant, right? And this component is nothing else but this times sine of theta. Okay, this is the direction of the centripetal force. I need to find out this component, right? So this component is the resultant times sine of theta. This is nothing else but the force applied by the spring on this mass m. Okay, now if I see what sine theta is nothing else but L plus delta L divided by P. If I put in this value of sine theta in here, I get m omega square times L plus delta L is equal to x times delta L. Okay. Let me solve for it now. I'll get L divided by delta L plus 1 is equal to x divided by m omega square, okay, which gives me L divided by delta L is equal to x by m omega square minus 1, which gives me delta L by L is equal to 1 by 1 by x by m omega square minus 1. In the question I have been asked to find out delta L, but in reality they should have asked delta L by L, because it depends upon the initial length of the spring as well, because theta depended upon that. I think that is one small mistake in Irodov. But yeah, I mean, if I consider L to be unity, I would get delta L as 1 divided by x by m omega square minus 1. So this is what my answer is going to be. This question looks intimidating in the first instance, but if you read the question thoroughly, you'd be able to solve this question pretty easily. And that is the case with most physics problems. If you read the question properly, you would be able to solve the question pretty easily. So these are the two questions that we solved today. We'll come up with more problems in the next class. Alright, bye.